Hello, my name is Ivan Taylor and I'm from Ontario, Canada. And I'd like to present to you today some work that some colleagues and I are doing on system dynamics support to resilience analysis of a complex system. And the team consists of Ken Cureton from the INCOSE Systems Engineering Organization. He is the chairman of the Resilient Systems Working Group. Francisco Araujo is a modeler who did most of the work to develop this system dynamics model, and Suraj Kul helped us write up this work as a book chapter for Springer. It'll come out in the new year. Today I want to start with some definitions and then get into the problem that we looked at and the approach we took, which was a system dynamics approach. I'll present the model that we built and provide some example results. And then I'll close with some concluding thoughts. So this is a picture of resilience, of how resilience can be visualized. We have a system here that delivers a capability. However, this system is affected by an adversity which stresses the system, and then if the system is resilient, it can continue to provide the required capability. The definition of resilience is the ability to deliver required capability when facing adversity. The scope of resilience includes the ability to avoid, withstand, and recover from adversity. And resilience, system resilience considers all engineered systems, including cyber physical, organizational, and conceptual. This is a picture of the resilience timeline that was developed by the Resilience Working Group of INCOSE. And this is, you can see that we have time on the x-axis and the capability on the y-axis. And the system is performing at a certain capability in equilibrium for a period of time. And then at a certain period of time, some adversity occurs that creates a stress on the system, and that causes the capability, the delivery of the capability to decline for a period of time when it's possibly below the required capability. And then if the system is resilient, it will begin to recover after the stress ends and be able to get back to a state above the required capability and then continue its growth in capability till it gets back to the original delivered equilibrium. And this model, this timeline is very appropriate for a system dynamics model, because system dynamics uses behavior over time graphs where time is on the x-axis and the measures of performance are on the y-axis. And I'll show you many behavior over time graphs in the following slides. Now, we also took a transdisciplinary approach, and this transdisciplinary approach is defined as exploiting the growing convergence between engineering and disciplines from the sciences and humanities to solve complex scientific and societal problems. And INCOSE is focusing on transdisciplinary engineering, systems engineering, for the next few years. The different disciplines, it reaches beyond engineering to other disciplines. For example, human cognition and behavior from the psychological sciences, group dynamics and culture from the social sciences, bio-inspired engineering from biology and medical sciences, cost and trend analysis, real options from the financial and the marketing disciplines. Um, it also tries to identify and leverage new concepts and relationships to potentially make complex systems problems tractable and amenable to cross-disciplinary solutions, including using novel, unprecedented systems and options, using advances in machine learning and artificial intelligence, with using hyperconnectivity and the Internet of Things, using cyber-physical human systems integration, and using advanced modeling techniques integrated in the life cycle processes. So we looked at a particular problem using this idea of resilience and this idea of a transdisciplinary approach to a complex problem. So we looked at the ability to analyze and manage the competing capabilities that are involved in the development of the Arctic. That is, that's the exploitation of its natural resources and the use of the Northwest Passage for shipping. We also want to, at the same time, sustain the environment to support native and natural life. So these are competing objectives, competing capabilities that the system should be able to develop if it's going to be sustainable. The intended audience is the government regulators and policy makers. Now, we used a system dynamics approach, which tries to develop a digital twin, and that is a computer simulation of a real-life system. So we tried to develop a computer simulation of the Arctic, development of the Arctic. And system dynamics is a mathematical formulation of a system, a numerical solution to a system of highly interconnected first-order differential equations. And as I mentioned, it looks at behavior over time of important measures, and these behaviors can involve growth, decline, equilibrium, better before worse, and worse before better. And those last two behaviors are interesting because they show the difference between the short term and the long term in the performance of the system. Also, system dynamics approach utilizes both quantitative and qualitative measures, but it requires unit consistency. So everything has to be defined in terms of some measures or units of measure. And we look at, we're going to, often in system dynamics, we look at recovery from shocks to the system. So we built a model, and I'll give you a top-down view of the model. It has aspects of the environment, which involve the land, the ocean, and the ice, as well as wildlife and fish. It has a model of the people, including the native population and the non-indigenous people that arrive in the Arctic and try to exploit the resources. And it involves a modeling development and sovereignty, which involves the building of infrastructure and the shipping through the Northwest Passage. So, as I said, system dynamics involves a highly interconnected first-order differential equations. And you can see here that we have these 6 sectors or 6 submodels that involve in this, you can't really see it, but in this sector, we have the environment. In this sector, we have wildlife and fish. In this sector, we have the development. In this sector, we have shipping. In this sector, we have the non-indigenous population, and in this sector, we have the native population. And you can see that these sectors are highly interconnected, both inside and out and between each other. However, we are able to produce this simple performance measurement matrix that involves 4 quadrants of performance. So the system starts at the point 1, 1, which is equilibrium. And then over time, it moves into one or more of these 4 quadrants. So the ideal situation would be for the system to move into this upper right-hand quadrant that involves improved economic health and improved environmental well-being. The area to avoid is this lower left-hand quadrant that involves reduced economic health and reduced environmental well-being. And then we have these trade-off quadrants where we have improved environmental well-being, but degraded economic health. And we have in this lower quadrant, we have improved economic health, but reduced environmental well-being. And we look at shocks to the system where the system begins in equilibrium, and then at a certain point in time, there is a step function that involves a change in the system or a change in one of the parameters that introduces, say, a new policy that then continues for the rest of the time period. And the shocks that we considered were sea level rise, non-indigenous arriving and leaving rates, wildlife birth, death, migration rates, and poaching, fish birth, death, migration patterns, and catch rates, environmental degradation and regeneration rates, ice freezing and melting rates, infrastructure building and demolition rates, shipping routes opening and closing rates, and ships commissioning and decommissioning rates, and the fraction of ships that are supporting the fishing industry. Now, we developed an interface for the model that is in the Stella Architect software, and we can see here the quadrants system over here on the left, which involves, this is for the baseline case of unconstrained development, which introduces economic growth, but environmental degradation. And here we can see infrastructure growing exponentially because the income is generated by the infrastructure that is built in the Arctic. And then we have these policy levers down here that we can turn on. There's over here, we have environmental protection levers. And over here, we have native empowerment levers or policies. And here we have development and sovereignty policies. So we can flip on these switches to turn on these policies at a certain point in time. Here is the results of unconstrained development for a 75-year period. And we can see that the shipping routes and the ships are going up. The population, the foreign population is going up and then reaching equilibrium. The native population is dropping, air pollution is increasing, fish banks are decreasing, wildlife is decreasing, environmental health is decreasing. But the zone attractiveness is increasing, and that is the attractiveness of the Arctic for development. And here's the smaller view of the the performance quadrant. So we looked at different policies, and we turned on a number of native empowerment policies and environmental protection policies. And we ran the model out with unconstrained development, but we introduced the policies at year 40 of the 75-year period. So the degradation begins to show up in the first 40 years. And then the question is, could we introduce policies such as native empowerment and environmental protection that can return us to this optimal quadrant where we have improved economic health and improved well-being? And we can see that there are some policy settings. Basically, we ran 25 settings, 25 sets of policy settings, policy parameter settings for when these policies were turned on at year 40. And we found that there were some policy setting combinations that led to this ideal state, but many of them ended up in this trade-off state that resulted in improved economic health, but reduced environmental well-being. And this blue line is the unconstrained development without any native empowerment or environmental protection. And here, this shows the unconstrained development with native empowerment and environmental protection, and for a number of the parameters. So here we see shipping routes and ships are unaffected by this because we have unconstrained development. Air pollution is unaffected. However, the 25 policies are shown here in the foreign population or the non-Indigenous population, and we can see that the native empowerment leads to, most of the time, growth in the native population, and often very good results for the fish banks, and also some results that are positive for the wildlife. However, the environment as a whole tends to be reduced over time with these policies. So we believe that these policies of native empowerment and environmental protection may not be sufficient to restore the Arctic to a higher level of environmental well-being. So then we looked at adding development constrained by government regulation. And we got this picture. The blue line, again, is the unconstrained development with no native empowerment and no environmental protection. And when we add government regulation to the mix of native empowerment and environmental protection, we can see that the environmental well-being increases in all cases. However, when the regulation constrains the development of infrastructure and shipping too much, then we see we end up with a lower level of economic health. So we want to avoid that where possible and get into this ideal state where we have improved environmental well-being and improved economic health. So you can see there's a number of policies there, and there's a large number of policies that improve the environmental health without reducing the economic health. And here is a closer look at the variables. We can see that the 25 runs show variations in the shipping and the ships and the air pollution. There's more variety here in the fish banks and the wildlife, and the environment then has changing directions depending on the parameter settings. So if we go back to the reliance timeline, we see that we have a system that started in a baseline case, and then had some development that caused the system to degrade environmentally, and then policies were implemented to restore the environment to a required above required capability, and then we end up with a positive situation over a period of time. So concluding thoughts, we realized that the Arctic is a complex and fragile system. And there are many stakeholders with competing objectives with regards to development of the Arctic. So there's the native population who are protecting their way of life. There's the industrial developers who are trying to produce economic income and economic value for in the development of the resources and the shipping routes. There's also the environmental protection agencies that are interested in protecting the wildlife and the fish. There's also government who are interested in promoting and maintaining their national sovereignty over the land and the sea around the land. And so these 4 groups of stakeholders were considered in our model. And we built a transdisciplinary digital twin to conduct experiments on the impact of development and the impact of policies to try to make the system more resilient. And this digital twin was based on a highly interconnected system dynamics simulator. And there were policy shocks to the system that we modeled. And we tried to show here how system dynamics can be used to design a resilient system for the future. If you have any questions about this, you can reach me at this email address. And I'd be very happy to talk to you more about system dynamics and resilience. Thank you very much for your time.